All right. Hello, everyone. Welcome back to Physical Geology 1403. We're already in week 3. Yeah, time is flying, isn't it? For those of you watching this in the future, we have had some pretty bad weather outside this weekend. It's been raining almost nonstop for about 30 hours now. And where we live in Odessa, Texas, there's terrible drainage for reasons that we will actually talk about today. Yep. And so the water just kind of sits and collects and floods. We get bad flash floods. I was in Walmart yesterday. I walked into Walmart and the water was ankle deep. I came out 30 minutes later and the water was up to here in the parking lot. I had to slog through water halfway up my thighs to get to my car. But luckily I drive a Jeep, so I was able to leave just fine. But tons of other people were not so lucky. All the sedans in the parking lot had water up to the driver's windows. And then those are all the people stuck in the store. Okay, so we also are down to, for now anyway, 2 students in the classroom out of the 13 I typically have in here. But we'll still have fun, make it as interactive as possible. You guys will just have to answer all the questions. Yay. I also am not going to be wearing my snake today. It is a little too cold and chilly for him. He's kind of curled up in a ball under his heat lamp, and I'm going to be nice and leave him there today. All right. So today is lecture 5, but before we jump into the new stuff, I, as usual, want to open up the floor to any questions y'all have about what we learned last time. We learned about igneous rocks, intrusive activity, and volcanic processes over the last couple of lectures. Any questions about all that?
Not yet.
Not yet. Okay. To be determined. Fair enough. Okay. Any questions about the class in general? Or about anything occurring in the world right now? Tonga's had a couple of earthquakes recently.
Is it true that this winter's going to be pretty rough? Or?
This winter? You mean about for us specifically here in West Texas? Probably going to be pretty rough, yeah. As more time goes on, we are finding that the extremes of weather are becoming more pronounced. Extremes becoming more extreme, you could say. So while sure, every other year or maybe 2 out of every 3 years tend to be mild, the extremes that we get on each end of the spectrum, when it is dry, it's real dry, right? And when it is a rough winter, it's a really rough winter. We're seeing the extremes gradually move further and further down the scales. So it is very possible that we will have a very rough winter this year. We'll see. We had kind of a rough summer. Lots of 102 plus days this summer. Very little rain. There's a rainfall we've had this weekend is the most that we've had for the entire year, and it's the beginning of September. So if that's any indicator, it's very possible that we will have a very hard winter, yeah. I have no way of predicting if it will be the same as 2021. 2021 was what we here call a snowmageddon, which is really funny because snowmageddon here was, what did it come down to? 8-9 inches of snow, something like that. That's not even a snow day if you like go up to Alberta or northern New York. It's just all right, that's fine. Just the school buses go behind the plows, you know? Here it's very different. We're not acclimated to it. People here are very sensitive to the cold, and none of our infrastructure is acclimated to the cold either. For instance, here, you only have to bury your pipe, your water and gas pipe, 3 feet under the soil. So when it gets below freezing for an extended period of time, those pipes freeze and break. That's a big impact that we had from Snowmageddon here in 21. Places that are more used to heavy snowfall and long freezing conditions further up north, you have to bury your pipe 6 feet deep. That keeps your pipes from freezing under typical conditions. So whenever those extremes do happen here, they are really, really bad for our infrastructure, which is why people lost drinking water and homes couldn't get heated, and why they had to bring in aid and all of that. It was rough for those couple of weeks. My family and I had actually just moved from Montana the year before, so we still had a lot of our cold weather gear and a lot of our cold weather stuff. Still had space heaters. We had, all our heavy stuff. It was good. We did okay. I was actually the only person on the road coming here to campus. I was the only person here on campus for those couple of weeks because I had no problem driving in the streets. All right. Yeah. Any other questions? No? All right. Well, let's jump in. We are leaving behind the world of igneous rocks for now and talking. This is my friend Jennifer. She works in the STEM center down the hallway if you guys ever need tutoring for anything. We are entering the world of sedimentary rocks. But before we talk about sedimentary rocks, we need to talk about sediment that they are formed from, right? Where does sediment come from? How is it made? What different kinds are there? All of that. That's what we're discussing today, okay? So before we can understand sediment, let's talk about the processes that make it, namely weathering. Now, weathering is the breakdown of material. Any material, really, when it breaks down, you can call that a form of weathering. If you've ever read an older book, maybe like a Jane Austen novel or anything like that, they'll use that word, weathered, or maybe like a Western novel. He had a weathered appearance, that's kind of an adjective that you use to describe someone or a thing that looks old, kind of broken down, like, aged. For a person, it might, wrinkly, kind of windburned, someone who's been outside a lot. That's the word you would use to describe them. And that's not far off from the way that we actually use it in geology as well, okay? Weathering is the process of a substance breaking down under the influence of its environment, okay? This is one component of dynamic Earth. Earth is dynamic, right? Characterized by that constant change in activity. Weathering is a constant aspect of that. Things are never not weathering. All around you, things are weathering down, although slowly to the point where you can't tell most of the time, but it's still happening, okay? Now, this is a fundamental characteristic of another thing we talked about, the principle of uniformitarianism. I used the principle of uniformitarianism to prove to you, or to show you, I should say, how sometimes a large thing can come about over a single process that happens over a long period of time, like the Grand Canyon, where the Grand Canyon originally was, at one point in the past, was a stream. And then that stream turned into a river, and then various tectonic processes happened, and boom, bada boom, millions of years later, we have the Grand Canyon. But from weathering, that's how that happened. Breaking down material through a process, in this case, a river's movement. Okay, we'll talk about that today. Some other examples. Plants. Plants grow, and as they grow, they expand, and they break things apart. They crush rock. They split rock apart. They move material, right? Or let's talk about how a plant itself can break down. A plant dies. It falls on the ground. What happens to it? It decays. It falls apart. It rots away, right? You ever walk through a forest? We don't have many of those around here. But you ever walk through a forest and you found like a rotting tree stump or a log that's obviously just been sitting there for years and it's covered in, mushrooms and all these beetles running through it, and you just poke it and it falls apart? You can call that a process of weathering, okay? It is breaking down as a result of the environment that it is in. Rust. How about rust? That's metal weathering away. In the case of rust, it's usually, if you're thinking of that red rust you get when you have iron, it is oxidizing, okay? There are oxygens binding to those irons and creating a new thing, okay? In an attempt to reach a certain state of stability because of that environment. It is bonding, right, with those oxygens. You get ferrous oxide as opposed to just iron. Okay. Now, that's just a couple of examples. There are many forms of weathering. We're going to focus from this point forward just on how minerals weather, and therefore how rocks weather, which are made of those minerals. Okay. Now, this is an external process. Okay. Remember, we have two sources of energy for all the processes that occur on Earth. The sun powers the external processes, of which weathering is one. And then you've got the energy coming from inside the Earth as a product of its residual radiation, okay, from all of the highly dense, highly radioactive elements way down there in the mantle, okay, or in the core, radiating out into the mantle, and some of it makes it up here to the crust. Those are the two sources. Weathering is a superficial process, therefore it is powered by the sun. Now, weathering, again, is that breakdown of material, much like how this chisel is being used to break apart the rock. Think of this as a form of artificial weathering, if you will. Energy is being given, and that energy is breaking that rock apart, okay? Now, I want to make sure that you understand something very important here, something very fundamental. People will often confuse weathering and erosion. You'll read some news article that talks about how a gravestone or how a mountain is slowly eroding away. This road is slowly eroding down. That is an incorrect use of the term erosion. Erosion is the transport of already broken down material. What do we call the breaking down process? Weathering. Bingo. Okay. Weathering is that breaking down process. Erosion is the transport of that weathered material. Okay. So you've got your weathering and you've got your transport. And this river, look at how much dirt is in that river, how much soil, how much sediment. It's brown. It is eroding that material downstream. So erosion is the transport. Now, one form of erosion is called mass wasting, which is this little video right here. Come on. Nope, not what I asked you to do. Where's my mouse? There it is. Okay, let's play that again. Mass wasting is the gravity-driven form of erosion. There's no water pushing this. Wind didn't shove it over and isn't carrying it anywhere. What happened? It fell under the influence of gravity and gravity alone. That is called mass wasting. That is a form of erosion, which we will talk about later on in Module 2 when we discuss landslides. Okay?
So erosion is not actually the material itself either. It's actually just the method by which.
Great. Yes, so his comment was, erosion is not the material itself either. No, it is not. Erosion is a process like weathering. It's like, if I made a sandwich, I'm in my kitchen, I'm slapping that sandwich together, right? That's me making a rock. Think of it like that. The rock has been made through one process or another. I have made that rock sandwich. Delicious, right? But I know that me and my two buddies need to eat this sandwich, and so one sandwich isn't going to do us all any good. So I chop it into 3 pieces. I am removing pieces of the sandwich. I am cutting it apart. Think of that as the weathering. And then I have to carry plates of these pieces of sandwich to each of you, right? And now we each have our sandwich, but it has been spread out through the process of me taking it and giving it to you. Think of that as the erosion, okay? All of these are 3 different processes involved in this rock, in the life cycle of this rock, you could say. All of them involving the same material, but different things are happening along the process of all of these things. You got that? Does that make sense?
Mass wasting is one of those dropping.
Mass wasting, yes. Okay, and we will talk about mass wasting in more detail later on. Okay, when we talk about in Module 2, it's pretty much all talking about superficial processes. Okay, we're still in Module 1, so we're not going to go too deep on that right now. Okay, I do need to explain weathering and erosion to you before we talk about sedimentary rocks, or else our conversation about sedimentary rocks doesn't make a whole lot of sense unless you know where that product is coming from or where those ingredients is coming from. if that makes any sense. Okay, cool. Perfect. Now, sorry to bring up sandwiches right before lunchtime, by the way. It's just food. I cook a lot. I make a lot of food. It's just the examples that come to my head. All right. There are two types of weathering we're going to learn about. The first one is mechanical weathering. Mechanical weathering is the physical breakdown. Okay? I sliced that sandwich. Gosh, I'm going to keep coming back to that. Okay? I sliced that sandwich. You physically break a rock. I take a hammer. I smash a rock. That's mechanical weathering, the physical breakdown. Big pieces into little pieces, right? Easy to understand. Now, here's an interesting thing. If I were to take a mass of a rock and physically weather it down into, like mechanically weather it down into smaller pieces, it's going to speed up the rate at which it breaks down. The more small pieces I have of my original mass, the faster that mass is going to break down. Why do you suppose that is? Let's say we're preserving the same mass. If I have 1 kilogram of rock and I break that into smaller pieces, I still have 1 kilogram of rock. It's just in smaller pieces. But the rate at which these are breaking down will increase, even though I am saving the same amount of mass. Why would this be?
Because the pieces are smaller.
The pieces are smaller, but what does that mean for the mass as a whole? Why is it more susceptible? What is there more of? I'm keeping the same amount of mass. What is there more of, though? Okay, you get what I'm asking? What are the words I'm wanting you to say then? It's all the same material. All of these pieces are equally stable or unstable, as the case may be. If it's weathering and breaking down, it's unstable in its environment, right? Yes. If I am keeping the same amount of mass, why is the rate of weathering increasing as my pieces reduce in size?
There's more weathering happening to each.
But why is there more weathering happening to each piece? Okay, yes, you are correct. There are more pieces. What does that mean? I'll show you the word for it, okay? Here I have my rock, that one single unit, okay? We're preserving this exact amount of mass. Let's say this rock equals 1 kilogram of mass, okay? It is 4 square units to the side. It doesn't matter what the units are. These could be inches, these could be feet, these could be kilometers, right? 2 by 2, 4 square units to each side, right? That gives me 24, because this is a cube, so there are 6 sides, right? 24 square units total of surface area exposed to the conditions that will weather it. Now let's say that I mechanically break this down into smaller pieces, each of which is 1 unit to a side. Okay? That gives me 8 cubes, each of which has 1 square unit on each side. Now I have 48 total square units of surface area exposed. This is the word you're looking for. Surface area. As you reduce the sizes of your pieces, you are therefore exposing more material in the form of surface area to those weathering conditions. Let's say I reduce those again. We go from 48 total square units to 96 square units if each one of these blocks is half a unit to a side. So even though my pieces are getting smaller, because I'm talking about the same amount of mass, I go from this big block to these little blocks. I am having more surface area exposed. More surface area exposed means weathering goes faster because the weathering can happen on more surface area. I only have 24 potential square units on this one unit, this one block that I can weather. but I have 96 square units of surface area on all of these combined that can be weathered. And so as the pieces get smaller, the rate of weathering increases. Following that logic? Yes, it's surface area. Okay. Now here's another little thing. Corners tend to have more surface area than a side. Because on a corner, on a side, I've just got this one area that can be weathered at any given time. On a corner, I've got that side and that side and that side that can all be weathered simultaneously. So my corner is gradually going to become weathered down until it's not a corner anymore. It is rounded off. Can that explain anything that we know about, say, when it comes to river rocks or rocks you pick up at the beach? What do you notice about all of those?
They are rounded off.
Yeah, they are rounded, right? They're smooth, they're oblong or circular, almost like balls, some of them. But the one thing that you hardly ever see on a rock you pick up from a river is a corner. They're usually nice and smooth and rounded. We call that river stone. Why? Because of this simple concept. Corners have more surface area, therefore they weather faster, and your rock becomes rounder over time. Make sense? Great. All right. Some different types of mechanical weathering that you will see typically. Frost wedging. Frost wedging is what happens when water percolates its way down into some rock. There's these natural cracks and crevices. Rock itself often has some amount of porosity in it, especially if we're talking about, say, vesicular igneous rock, like what we learned last time, or sedimentary rock, like what you'll learn about next time, tends to have a lot of pore space. Regardless, the water works its way in there. And as the water makes its way in there, what's going to happen to it when the air temperatures, the ambient air temperature goes below freezing? It's going to freeze, and then what happens? It expands. Bingo. Water expands when it goes from liquid to solid. It's weird that way. A lot of other things will actually contract. They will take up less space when they go from a liquid to a solid. Ice is different, and we will talk more about this concept when we discuss glaciers in the next module. But it expands by roughly 9%, okay? Come on, camera, stay with me here. There we go. It expands by about 9%, okay? And as it does so, what's it going to do to that rock that it percolated its way down into? The ice needs to expand, and therefore it's going to do what to the rock? Yeah, it's going to push that rock. It's going to crack it even more. It's going to force that crack, that crevice that it leaked down into, it's going to force it a little wider. And as that happens, thaw or freeze thaw, freeze thaw, freeze thaw, year after year after year after year. And eventually those cracks widen out enough that pieces of rock will just fall off. They will be broken off of the whole mass of rock itself. This is called frost wedging. This is a form of mechanical weathering. Another way, salt crystal growth, okay? These little pockets you see in this rock, that's what happens when you have a body of rock that is somewhere near a salty body of water, say the Dead Sea, for example, or the Great Salt Lake in Utah, okay? Or the ocean, right? Easy example, huh? The ocean, yeah, it's pretty salty. If you've ever been there and you took a nice swig, you've probably found it to be pretty salty. Okay, so when the water kind of laps up on that rock, it deposits some water, salty water there, and some of that water makes its way into those natural cracks and crevices, but then that water evaporates away and leaves behind what? Salt, bingo. The salt can't evaporate away, right? If you've ever purified salt water, what's the best, easiest way to do that? Evaporate the salt water. You get fresh water as a result, and you leave behind a little crust of salt, right? None of that salt makes it into the evaporated water, and so it's left behind. And so when that happens in the rock, over time, you get to start growing salt crystals in the rock. And these crystals will do something similar to what the frost did, where gradually over time, it'll fleck off little bits and pieces of rock until you're left behind with these little cavities, these pockets where that process occurred. Okay. Other forms of mechanical weathering. Sheeting. Sheeting often happens to igneous plutons. Who can remind me what an igneous pluton is? It's okay if you review your notes. You know how big I am on your notes. Highly recommend you take notes that you can rely on. And if this isn't in there, you may want to add it.
Did we talk about it in our last session?
We talked about it mostly in lecture 3 and a little in lecture 4.
Oh, we are on lecture 4?
We're on lecture 5. Today is lecture 5, no worries. Okay, an igneous pluton is what we call a magmatic body that solidifies underground. It has crystallized underground. I also refer to them as magma chambers, but that's when they're liquid. It's no longer a magma chamber if it's solid. At that point, it becomes what we refer to as a pluton. And you've got your massive plutons and your tabular ones, right? When you have a massive pluton, so a body of magma that is cool and crystallized underground, it has formed, that rock formed underground under certain temperature and pressure, under a certain temperature and pressure environment. When it is gradually pushed up or exposed at the surface, this can happen a few ways. Either tectonics forces it up out of the ground, or the ground weathers down to the point where it's exposed. Either one can happen, or both at the same time. When that happens, is my pluton now living? I say living very loosely, right? I'm not anthropomorphizing an igneous pluton, but follow me here. Is it under the same conditions at the surface that it was when that rock formed deep underground? No. What's different? What about the environment in particular? Pressure is a huge one. Temperature as well, but pressure is the big one. When it formed deep underground here, it was under certain pressure. Now that it's exposed at the surface, it's under far less pressure. And so as a result, my rock that formed under high pressures is going to start expanding outward under the lower pressures. And it's going to crack and form this sort of sheeting structure where it looks like layer after layer of eggshells are falling off. It kind of looks like you took an eggshell off of this, and there was another eggshell under it, and then another eggshell under it, and then another eggshell under it. That's what it looks like, right? That's sheeting, okay? This happens very commonly to igneous structures that are exposed at the surface. And then finally, biological activity can cause mechanical weathering. Take a look at this tree. This tree probably started off as a seed stuck in this tiny little crack on this cliffside. But as time goes on and it grows, those roots are going to reach deeper and deeper and deeper into that crack. And as they are growing, they're going to force that crack wider and wider and wider over time until finally this block is eventually going to fall off that cliffside as a result of the activity that this tree did. Not because of lower pressure, but because that tree is slowly forcing this chunk of rock further and further away from the main cliff here. Okay? As time goes on, this tree gets taller, it also gets wider, and it's going to widen that crack down there as well until gravity takes over and whoo, bye-bye. Okay? Biological activity can absolutely contribute to mechanical weathering. Any questions about mechanical weathering or any of these examples? Do we count? Ooh, that's an interesting question. We are both forces of weathering and erosion. If I put a stick of dynamite in a cliffside and blow it up, is that mechanical weathering? Yeah, why not? Right? Now, is it biological because I put it there? Not in the same way that the tree is, right? Well, would I classify a stick of dynamite? I don't know. It's definitely mechanical weathering of one kind. I don't know that it would necessarily fit into any of the categories or any of the examples that I gave you. Well, you probably could make the argument that it is biological to some degree. Whereas if
you were walking in a desert before.
if I walked up to the edge of the Grand Canyon and I found a rock that was kind of still attached to the cliffside, but I could stomp on it enough that it would fall off, that's probably a form of biological weathering because I did that. I exerted my own energy to do that. Far less connected to the biological activity than a stick of dynamite is, right? I don't know where I would put a stick of dynamite on there. Definitely mechanical. I don't know that it would necessarily be biological, though. Okay. Interesting question.
It's the same, like a similar application to like ice.
To ice.
Stepping on ice and
Well,
breaking apart.
Connected to ice how? Sorry.
Well, I'm just saying as a mechanical weathering process. Well, I guess ice is really.
It is frost wedging. Frost wedging, that first
No,
example
like
again.
like a lake.
Oh, you're talking about breaking ice?
Yeah.
Because ice is a mineral. Yeah, I guess if I took a hammer and I broke up ice.
No, but I'm talking about like stepping onto it, like a lake.
Yeah, and then you break the ice by stepping on it. Yeah, you could call that biological weathering because I am doing it and I am biological. It is a process of my body. Yeah. Interesting questions. I like it when we dive a little deeper into the philosophical. Okay. Let's move on to chemical weathering. Chemical weathering is what happens when you have material that rather than being broken apart physically, dissolves instead. Okay, so instead of breaking things apart physically, they are breaking apart at the molecular level. We are breaking bonds. Okay, so some common examples of how this can happen. Rust. You get oxygen dissolved in water, right? You get those free oxygens in there. They can bond easily with iron or other metals. Different things rust in different ways. Copper turns green, right? That's why the Statue of Liberty is green. It used to be copper colored. It used to be this color right here, right? But now it's green because so much time has passed that the exterior surface has bonded with a lot of oxygen, yada, yada, yada. There's more to it than that, but that's just it in a nutshell. Iron turns red. There's all sorts of different ways that different things can oxidize. Same process, though. Same fundamental concept, okay? That is an example of chemical weathering. In lab 1, you all also observed a form of chemical weathering when you put, or you watched me put, hydrochloric acid on minerals. That acid probably started dissolving most of those minerals. It probably had a reaction with most of those minerals so you couldn't see it. There were a few that had far more obvious reactions, that bubbling effervescent effect, right? That's an obvious reaction. You're dissolving that mineral, right? Now, it doesn't have to be hydrochloric acid. There are acids that are far more commonly found in nature, in particular, carbonic acid. You probably drink some degree of carbonic acid every day and don't even realize it. Very light carbonic acids, you aren't going to notice. It's just part of your water. What do I mean by carbonic acid? When carbon dioxide is dissolved into water, it makes a light carbonic acid. This will react stronger with some minerals more than others. That same mineral that we talked about before, calcite, the one that reacted to hydrochloric acid, surprise, surprise, it reacts very strongly to carbonic acid as well. How does it react? It dissolves easily. This is why there are lots of caves in places like the Guadalupe Mountains. It's mostly limestone. We'll talk about why that is in our next lecture. In Florida, pretty much the entire state of Florida is nothing but limestone made out of calcite. And so there's lots of cave structures under Florida, right? Many of these caves are in fact formed by the dissolving of the calcite in their limestone when carbonic acid is introduced to that layer of rock. So how does this happen exactly? Well, you got clouds of water, right? Those clouds of water are interacting with carbon dioxide in the atmosphere. More carbon dioxide, more carbonic acid. This gets us into the realm of climate change and all of that, which, believe me, we will get into. Regardless, as the concentration of carbon dioxide in the atmosphere goes up, the concentration of carbonic acid that falls in rainfall also increases, okay? So you get carbonic acid in your rain that falls to the ground, percolates down into the water system, and as it goes, it dissolves calcite on its way. And you end up with cave networks, okay? Most of the caves that I will go into over the course of the year are made using this method. Some of them were made with from a more sulfuric acid because of near contact with volcanic activity, but most of them are made through carbonic acid processes. Okay, so why does this happen? If anyone's interested in the chemistry, here you go. Here's your calcite, CaCO3 right there. Then you got your carbonic acid, which is HCO3, and there's a loose hydrogen ion in there as well because we're balancing this with the water that it's in. And then you've got your calcium ion as a result, followed by what's called a bicarbonate. That calcium is usually utilized as dragged into some other bond with some other mineral, or maybe some other life form decides to use it, drinks it, and utilizes it. But this bicarbonate, 2HCO3 negative, that is called a bicarbonate. Have you ever got a glass of water, filled up your glass with water, and then left it somewhere? You took one drink and then you left it somewhere, and then you forgot about it for a few days and you come back and you're like, oh, it's gone, but there's a white film in there, like white dust in the bottom of your glass. If you have an RO system, you won't see this. More people don't have RO systems, I'm willing to bet, though. So most of you will know what I'm talking about. That white film, like you reach in there and you feel it, that white dust, that's bicarbonate. That is the product of carbonic acid breaking down calcite. Okay, it's in almost all water everywhere. It doesn't really hurt you unless you get a lot of it. If there's a lot of it in your water, it probably will contribute to your kidney stone problems. But like a little bit of it in the water is pretty common, won't really hurt you that much. Okay. Now, calcite is not the only mineral that will react to carbonic acid. Matter of fact, most of them will, given enough time. For example, here we have potassium feldspar. Potassium feldspar, a very common ingredient in granite, right? I held up that chunk of granite the other day. Here it is. That pink feldspar, that's potassium feldspar. It's pretty common. So here we have our potassium feldspar, K potassium, Al aluminum, Si308. That Si308, ooh, look at that. That is our silicon tetrahedron framework. Okay, and then there's a potassium and an aluminum attached to that. That's what makes this particular silicate mineral potassium feldspar. Okay. Then we've got our carbonic acid. It'll take two of them to complete this equation, plus the water that it's in. Then you end up with this, which I'll come back to in a minute, called clays. And then you've got a whole bunch of loose ions. Potassium ions, which are usually absorbed by plants somewhere down the road. Okay, they love those. Your bicarbonate, which we just talked about, and your silica. I'll talk about that silica in a moment. Let's come back to clay. Aluminum, silicon, oxygen, and some OH4s on there. Okay, this is a clay mineral. We talked about this in our second lecture. I introduced clay to you as a secondary mineral. I told you it is a secondary mineral. What does that mean? It is the byproduct of weathering silicates, not just feldspar. Its most common parent mineral, I guess you could say, is feldspar, but you can actually get clays from other silicates that weather down as well. There are lots of different kinds of clays, different variations, but they form through this process, the chemical weathering of other silicate minerals. Okay? These clays make the foundation of most soils. Okay? Fine grained soils anyway. There are sandy soils, but we'll talk about soils a little bit later. Now the silica, that silica ion flows away through the water until it finds somewhere that it can collect. Silica tends to bond with silica very easily. And so you get to start forming these chunks, these nodules of silica, filling in different holes and voids and cracks in the spaces in the rock. And that is how you end up with agates, like this. Camera, stay on me now. Agates like this are formed through this process. Silica ions from weathering, so tiny, tiny little ions that all came together and bound together in these concentric rings as it was filling in this empty space. Okay? We call that chert, by the way. You may also hear it referred to as flint or jasper. Those are all words for essentially the same thing. Okay? Now again, feldspars are the most common source of clays, but not the only one. Quartz, when you weather it down chemically, will make the silica ions that later go on to make that chert, those agates, right? Feldspars will weather down and make clays with excess silica, potassium, sodium, or calcium, depending on what type of feldspar it was, right? Amphiboles, okay? Those are going to break down into clays, but also limonite and hematite. Those are iron oxide minerals. And then you get extras as well. Olivine, which remember is that super dark, most of the mantle is made out of olivine, right? It's that first one we talked about that forms in Bowen's reaction series. When that breaks down, you only get iron oxide minerals out of that with a little bit of silica left over. So let me ask you this. Have either of you been to Hawaii? I know someone over here said that they had been to Hawaii before last week. Well, then you'll have to take my word for it. When you go to Hawaii, the dirt is red. Using this logic, tell me why the dirt is red. Hawaii is made out of what kind of rock? I'm going off of what you're saying here. Yes, it's definitely igneous rock. What kind? Talked about Hawaii over the last couple of lectures. Yeah, it's definitely going to be made out of minerals, but I'm asking the igneous rock that Hawaii is made out of, what composition is it? How about that? You remember we learned about igneous compositions? Mafic, felsic, intermediate, so on and so forth. Ferric? Ferric means it's rich in iron, but that's not one of the compositions. A mafic, yes, it is made from mafic igneous rock, which means that it is rich in iron and magnesium, okay? It's mostly made out of this rock. Do you remember what this is? A'a is a word that we use to describe a way that this can form. But this particular kind of rock is this. It is mafic, in fact, it is mafic, and it is aphanitic. What is the most likely answer for a mafic, aphanitic, igneous rock? Not obsidian, that's glassy. This is aphanitic. Microscopic crystal sizes, Most of these minerals are dark silicates, which is why this is mafic. Talked about this rock quite a bit in the last couple lectures. Basalt. Basalt. Hawaii is made out of basalt. Okay? Pretty much exclusively. What minerals is this made out of based on the fact that it is mafic? Would you guess?
You said it has a higher, they tend to have a higher iron and magnesium content.
Yes, they are iron and magnesium. They are dark silicate minerals. Which minerals in particular make basalt? Do you remember? Quartz is not going to be in there. Quartz is on your felsic spectrum for igneous rocks. Remember, your mafic ones, those iron and magnesium dark silicates, those are going to be the first ones that form in your magma chamber during Bowen's reaction series. Remember what any of those were? Not really feldspar. There's definitely going to be some feldspar in here, but that's not what I'm looking for right now. Huh?
Can you repeat the question?
Which iron and magnesium-rich minerals, those dark silicates, are going to make the majority of our basalt? When our magma chamber is still mafic during Bowen's reaction series. They're going to be dark colored, right? They're going to form early on. Our first one that tends to form, like I mentioned before, olivine. Darker green. There's probably some olivine in here. This is mostly black, though, right? Most basalts tend to be very black. They have a lot of pyroxenes. And there's probably amphiboles at some point as well. A lot of olivines and pyroxenes, amphiboles, dark silicates. What happens to these when they weather chemically? What do they become?
Was like the chart we were doing the other day with the M&Ms, right? Like they break down.
No, that's Bowen's reaction series. Now we're talking about chemical weathering. What do they become when they weather chemically?
Individual crystals.
Dark silicates are going to break down into a couple of things. Some of them are going to become some clays, like our amphibole here. But because they are iron and magnesium-rich silicates, there's also going to be iron oxides, limonite and hematite, like I mentioned before. What color do you imagine iron oxides are going to be?
Red.
What color does iron become when it oxidizes?
Iron? No, like orangish red.
Red! Oxidizing is a fancy name for rust, right? That's what's happening. That's all that's happening when something rusts. It's oxidizing. Oxygens are bonding to the exterior atoms on that surface and giving it a new color often as a result of that oxidization process. We have iron oxides as a product of the chemical weathering of our dark silicates. So you have clays plus iron oxides as a result of weathering basalt. Hawaii is mostly made out of basalt. Boom, bada boom. Follow that logic train. Hawaii's dirt is red. Do you follow that logic? Does that science make sense? Great.
Hawaii is made mostly of basalt.
Hawaii is made out of basalt, so its dirt's going to be red because it's dirt. It's, yep, you've got that iron oxide minerals like limonite and hematite. The soil's full of it because it comes from the basalt as it chemically weathers.
If you were to stick a magnet in the ground, it'd probably.
No, you're not going to attract dirt to a magnet. It's not magnetic, at least not to that degree. Okay, we will talk about the magnetism of basalt and dark silicate minerals very much later on in the class. It's actually the last lecture. Okay, actually it's the second to last lecture. And for you two that just came in, I am recording this. I will post it. It'll make a lot more sense. I might as well just repeat that. For everyone that's just coming in, this will all make a lot more sense to you after I post the recording later. Feel free to. Yeah, campus opened at 10. Campus opened at 10. Yeah.
They told us to be in the auditorium until 11.
Yeah, that's.
Most of us are about to.
Yeah, I don't get the high school announcements, so I didn't know that they told you guys to hang out until 11. All I heard was campus will open at 10 instead of 8, and so I was here at 10. That is okay. Yep. That is okay. We will adapt. Okay. But so I have been recording for about 50 minutes now. But again, you will be able to go and watch this. I'll post my YouTube link for you guys, just like I usually do. Okay. We're talking about, it's lecture 5 today. We're talking about mechanical and chemical weathering. Okay. So we're continuing our conversation about chemical weathering, which is the dissolving effect that happens on minerals when they interact with certain substances like acids. All right. So something that can happen, one thing that can happen when a substance is exposed to a chemical weathering agent is it's called spheroidal weathering. And it's weird enough that I thought I'd throw it in here and show you all a picture. This is what it looks like. Essentially, this is what happens when your chemically active agent kind of seeps in, kind of gets into your rock. Usually this will happen with something like a shale, which is a type of sedimentary rock you'll learn about next time. But it eats its way in there and then creates a chemical effect that causes it to bubble and swell upwards. And sorry for this gross comparison, but it kind of looks like blisters, like your rock is blistering upward and breaking off because it's cracking apart in those layers. Okay, this is called spheroidal weathering. Okay. All right. Now let's talk about the rate at which things weather. Just looking at these two gravestones, which do you believe is older, right or left? Right. That's obvious, isn't it? You're wrong. Sorry. Okay. This definitely looks older, and yet this one is the older one. Why? You looked at the date? If you can actually tell the date on that, that would be very impressive. This one is definitely older, but why does this one look like it's in worse shape?
It was a place that rains a lot.
It could be in a place that where it rains a lot. The environment that it's in has a big effect on how quickly it weathers, how quickly it breaks down. Also what? The material it's made out of. Those are the two big factors. What's the environment and what's the material it's made out of? You've learned all these minerals have all these different properties. And then you learn that different minerals have different melting rates. Not a huge leap to think that different minerals have different weathering rates as well, right? And what's the biggest factor in that? The environment that it's in, okay? So here we have a gravestone made from marble and a gravestone made from granite. The granite one is way older than the marble one. And yet, this one looks worse because marble is made from a very soft, very easy to weather mineral. One you're already familiar with, calcite. Whereas granite is made from a whole host of minerals that are far harder to weather. In particular, quartz. Quartz is a big component in granite, right? That's why we love it for our countertops. So you've also learned how to pick gravestones in my class. Hey, look at that. Okay. So big factors in the environment that will control how quickly they weather: your temperature and your moisture. Just like you said, Angel, how much it rains is a big factor because rain often has that dissolved carbonic acid in it that it picks up from the atmosphere as it interacts with carbon dioxide, and that carbonic acid is going to dissolve certain things faster than others. When one mineral dissolves faster than another mineral, by the way, we call that differential weathering. Remember we learned about partial melting last time, or 2 times ago, I should say, in lecture 3. Differential weathering is very similar, except instead of one mineral melting and another one not, one mineral is dissolving faster than another one is. Okay, that's differential weathering. All right. For the 2 that have been here the whole time, or for any of you that have just walked in, I know that you probably have a lot of questions. But before I move on to talk about soils, I just want to open the floor.
Can a lightning create rocks?
Can lightning create rocks? What do you guys think?
I mean, like it's fighting rocks and like breaking it.
Lightning's not biological, so it wouldn't be a biological process. Yeah, what do you think, Cade? When lightning strikes sand, it will actually flash melt and then almost instantly crystallize that sand. And you will actually have structures in sand. You can find them in the desert. You can go out in the desert and dig these things up, and they're in these crazy, wacky shapes as this lightning went through the sand, it flash melted it, and then it almost instantly crystallized. I forget what those are called. Yeah, they have a really cool name too. I don't remember what they're called. You can find them. It's not super common, but you can find them. I feel like it's something ectite or something like that. I don't remember. But yes, it's not necessarily a different. I shouldn't say that. It probably, yes, it's classified as a different mineral, but for reasons I'm not going to go into. According to our definition, it is still mostly quartz. So as far as you are concerned in my class, we'll not call it a different mineral, though technically speaking it is. Okay. Any other questions? I'm happy to see y'all. I was worried I wouldn't see y'all at all today. It feels a lot better in here now. I mean, I love you guys, but this is nice. I was about 50 minutes in before y'all came in. I'm not sure why the high school kept you guys an hour longer, but the college opened at 10. So.
Yeah, it opened at 10, but those classes got canceled for some reason, and to go to your 11th period.
That makes sense for the classes that are only 50 minutes.
Yeah, and that's what I told my principal. I was like, well, I have a lunch period, and he goes, just stay in here and don't.
Yeah, they probably figured just hold everyone to the same standard, and that would be easiest. So they did it out of consideration for the 50-minute classes, but that didn't take into account classes like ours that are almost 3 hours. Sorry that happened, but again, you can watch this recording on YouTube later to make up the difference. Okay, so let's start talking about soil. What is soil? Someone tell me what soil is.
I think dirt is the wrong.
Dirt? Did you say I feel like dirt is the wrong answer? Dirt is kind of the wrong answer. It's an answer though, so I appreciate it. What else?
I was gonna say dirt, but like.
Okay, dirt times 2. What do you got?
Isn't it like decomposed things?
Okay, so there's decomposed stuff in there. What else? Anyone else?
That's like protein.
As proteins? You gonna throw it in your morning smoothie? It has different minerals. Okay. Okay, well that's workable. Okay, so soil is essentially a substance that occurs on the surface, the dry portion of the surface of our Earth, I should specify, okay? And it is something that we rely on more than you probably realize, more than most people realize, okay? Soil is really cool because it is an interface of all of the spheres. Remember we learned about those spheres? The hydrosphere, the geosphere, the atmosphere, and the biosphere. Soil involves components from all 4 of those, okay? It includes mineral content, biological content, air, and water in varying proportions to each other, okay? Depending on the environment that it formed in, that's the biggest factor for what those proportion of those 4 things are, okay? So you've got your mineral matter, which is, comes from the mechanical breakdown of rock. And then you've got your biological matter, which we call humus. That is not hummus, by the way. It's not a delicious Middle Eastern dip, okay? It is humus, okay, 1M. That's from the decaying organic material. So it's mostly plants, but, animal matter does count as well, okay? And then you've got your air and your water. Those are pretty self-explanatory. Now, the balance of these 4 things will determine what can grow there. Let me give you an example. Do you imagine that the soil we have here in West Texas is in any way comparable to the soil in the Amazon rainforest? Absolutely not, I heard. Anyone want to contend that? We live in a desert. We'll talk about that in our next module. Do we live in a desert, though? We'll talk about that. Does anyone want to take the other side of the argument here and say that the Amazon and West Texas soils are similar? You'll take it? Tell me why.
Because if wait, you gotta give me here, because it's tough.
I'm giving you a minute.
Like, there is still, it has the same things, maybe not like the same balance, but like it's still the same minerals, humus, water, air.
He got it. Okay. True, the soil are not going to be identical between the 2 areas, but what Angel said is absolutely true. They are still going to have the same 4 ingredients. You are still going to have air, water, humus, and minerals in all soils. The only difference is the proportion. So while I may have a nice, black, airy, beautiful smelling Amazonian soil, and then I go outside and I pick up a handful of our red, orangish dust that we have here. They may not look exactly alike, but they are still going to have some proportion of the same ingredients, right? It's like if you went and you bought a hot dog in New York. Or here's a better example. Here, if you go and you buy a pizza from a pizza cafe in New York, and then you go to Chicago and you buy a pizza, nice deep dish, glorious pizza. I'm so sorry, I'm talking about food. And then you go to California and you buy a California style pizza. And you put those 3 pizzas out. First of all, never, ever, ever tell anyone from New York or Chicago or California that any of the other pizza is better unless you want to get into a fist fight, okay? Second of all, what do they all have? The same ingredients, just different proportions. Your deep dish pizza is going to have more sauce and toppings. It's probably going to have slightly thicker crust. Your New York style pizza usually has a thinner crust. Doesn't usually have much of a lip of crust around the outside either. Tends to be more of a flat style, okay? And usually less cheese as well. They like their more kind of Italian, authentic Italian looking pizzas, okay? And then your California pizza is going to look much different, but they're all pizzas and they all have the same ingredients, just different proportions. It's the same thing for soils, okay? In general, soil will have, ideal for general growing conditions, your soil will have somewhere around 25% air and water, although that can fluctuate freely. For example, the Amazon has far more water in the soil than we have here, right? About 45% mineral matter and about 5% organic matter. this is kind of, think of this as your plain vanilla soil, okay? We have less organic matter here. The Amazon has far more organic matter, okay? So let's talk about that mineral content. Where does that come from? Well, we already learned rocks and minerals, weather. They break down. That material gets carried away. We call that transportation. Erosion. Weathering and erosion are not the same thing. Weathering is the breakdown. Erosion is the transport. So at some point, your minerals break down. Those broke down minerals get transported away as sediment, and then it gets incorporated into soils somewhere. When you have a rock that breaks down and then that broken down material, that sediment is utilized for soil in that same area, we call that residual soil. So if a rock broke down here and then its sediment got carried over here and then used in the soil there, that's a residual soil. How do we know? We can test the chemistry of that rock to the chemistry of that soil. But if I have a rock, say, way up here, way upriver that breaks down, and its sediment is carried way downriver by the water and then used in a soil down there, we call that a transported soil, not because the soil got moved, but because the mineral content that made that soil came from somewhere else. It got moved. And we can tell that by testing the chemistry as well. Maybe all of this is sedimentary rock, but we can tell chemically that the mineral matter in this soil came from a metamorphic source. Well, the only metamorphic source is 200 miles that way, transported soil. Okay. Now, that's true to an extent, because as time goes on, you should be familiar with this concept now, as time goes on, things change, right? As time goes on, that mineral matter is going to resemble its parent material less and less. Why? Because it's constantly breaking down mechanically and chemically. It's being used by different plant sources. It's being pushed around by water. It's doing this, it's doing that. And as time goes on, it starts to look less and less chemically like its original rock. And so we can figure out where it comes from to an extent until it's very old, well-used soil, okay? Our climate is a big factor for what influences our soil. It's not the other way around. We don't have big forests of trees here in Odessa, Texas, not because our soil isn't conducive to it, but because the environment made a soil that isn't conducive to it, right? The soil doesn't decide anything. To be fair, neither does the environment, but the environment is the big controlling factor here. If we get very little rainfall, our soil is not going to have a high water concentration. It's going to have more air. If there are not lots of plants growing here, our soil is not going to have a lot of organic content, but you know what it will have? A lot of mineral content. And so we are going to have plants develop in this area that can survive best with low organic content, low water content, but high air and high mineral content. And so we get a lot of the stuff that we have in this area. We get a lot of, cactus, and we get some yucca, and we've got sage, and we've got the scrub. What do you call that scrub? It's on the tip of my tongue. It's like, it's got, with the spikes on it. You know what I'm talking about? The scrub that we've got out there with the big spikes on them. I don't remember what those are called. They're not fun. Huh?
Mesquite?
Mesquite. Is that what I'm thinking about? Oh, I know we've got mesquite. That might be the one with the spikes. I don't remember. Okay. Then we've got sometimes the biological input can also control what plants grow as well. For example, there are certain types of microorganisms that will either permit or deny the presence of certain types of plant life. Okay. So there's some fungi that live in soils that will attack certain type of plant life if they start to grow. Okay. There's also acids that can develop. Pine trees. You'll know pine needles, right? I love the smell of pine needles. Who likes the smell of pine needles? Those are awesome. Okay. When pine needles fall off of the pine tree and to the ground and decay and get incorporated into that soil, they introduce an organic acid into that soil. And that organic acid is hostile to most other forms of plant life, which is why if any of you have ever walked into a forest with pine trees, most of the plants you see around you are pine trees, with often wide spaces between the pine trees. There are some plants that have adapted, that have evolved to survive in that acidic soil, but it's very difficult to just grow anything in that soil. When my family moved to North Idaho, I had already moved out of the house by then. I was on my own. But my parents moved to North Idaho about 10 years ago. And when they went up there, first of all, big pine forest up there, right? It's like all pine, okay? And so they go up there, they have 10 acres. My mom wants to grow an orchard, a fruit orchard. She plants her first fruit trees. They all die in that first year. Can't figure out why. They were getting watered. Nothing was eating them. They had big fences around them, but her pears died and her apples died and all of that died. So they did an acid check on the soil and found that it was in fact very high in this organic acid, because think about how long pine trees have been growing there and developing that acid in the soil. Why is this a thing in the first place? Why do pine trees do this? It's an evolutionary mechanism that they developed a long time ago. A random mutation, take 1404, we'll talk all about this, but a random mutation in some gene of a tree in the past caused this acid to develop in their needles, which acidified the soil, killing everything but them. That's highly favorable mutation, benefiting only their species, and therefore it stayed in the gene pool, and it's still there today. Okay? So, my parents had to mix an acid neutralizer into their soil to make it so that they could, in fact, grow their fruit trees. Took a while, took a couple of years for it to finish, but now they have flourishing pear trees and apples. Every time I go to visit, I just gorge myself on pears. I love pears. They're delicious. Anyway, so that's an example of how the plant life in the area can also affect your soil. Okay, but the environment is the main contributor to the formation of your soils. Something else that can influence it, the topography. Topography is something that you probably don't know anything about right now, but believe me, you will become very familiar with it. Our entire Lab 5 is all devoted to topographic maps. Topography is the study of elevation, and a topographic map uses a flat two-dimensional surface to express a three-dimensional object like elevation. And you'll learn how to read that in Lab 5. But for now, topography just references the elevation and the angle of slope that an area has. Okay? If I have too much of a slope, am I going to have a good soil? What do you think? Who says yes? I will have a good soil on a steep slope. Who says no? I saw you be tempted there. You like being devil's advocate. It's kind of ironic, Angel. Okay. Yes, bad soils. Why? Why would a steep slope not have a very good soil, or an underdeveloped soil maybe?
Because soil is really loose. Material.
And therefore it's going to what?
Like low down.
It's going to fall down your slope. Soil is pretty loose. It's going to go down your slope. And where's the water going to be going? Downhill. So you're not going to be able to retain water in your soil. So you don't get very well developed soils on steep slopes. Bless you. However, what happens if I have a totally flat slope? I have absolutely no slope. It's totally flat. What's going to happen? Things are going to be dispersed. What's not going to be dispersed?
Not the water.
Water. Water has nowhere to flow. It's going to sit. It's going to saturate. You're going to get a bog or a swamp. Okay? So I do need some slope, Just enough to carry away excess water, but not so much that my soil gets carried away as well. Okay? Also, how much sun is my slope getting? I can't grow plants without sun, right? There are a couple of factors that are involved here in the development of these soils. Any questions? No? When I slice down vertically through my soils, I'm going to see several different colors show up the deeper that I go. These colors are often associated with the layer of soil, with a certain layer of soil, let me say. We call these layers of soil horizons. And there are lots more than this, but these are just the basic ones that I'm going to show you, okay? Our O horizon is at the very top. O, think organic. That's where your decaying vegetation is. Yes, go for it. Your decaying vegetation, that's where, if you're just kicking around in the leaves, you're looking at the O horizon of your soil, okay? More organic than anything else. Underneath of that, you have your A horizon. That's your prime soil. That's the good growing stuff. Camera, stay with me here. That's the good growing stuff, okay? That's got your mineral content and your water content and your air and your organic content. The O and the A horizon together are what we call the topsoil. That's where you grow all your crops. That's where most roots are. That's the good stuff. Underneath of that is the E horizon. We call that the E horizon, zone of eluviation, okay? Or leaching. Think of it as leaching. It's usually a pale whitish color, definitely paler than the soil above it. Think of that as the depleted soil. That's where the soil that kind of got used up fell or got shoved from here.
This is just funny to me because you remember how I remember last week I had my academic folder.
Yes.
We were going through all of this.
Oh, were you actually?
These past 3 weeks, that's been every section of mine.
That's funny. That's awesome.
So I hated that section. I heard one more thing about dirt.
She's going to lose it today, class. This is the day she snaps. No. So, sorry, I'm putting you through it again. Hopefully this is more fun experience than trying to memorize stuff for Academica. Under the E horizon is your B horizon, often referred to as the subsoil. Now, this is where you get a whole bunch of your fine-grained clays, the stuff that just cannot be used. It's too small. It's probably already been used up to an extent already. This is your very fine stuff. There's hardly any water. There's no organic content. It's just a lot of clays. And let me remind you something about the nature of clays. A clay mineral is flat. Okay. And so down here in our B horizon, we get a lot of clays piled every which way in that layer. Underneath of that clay is the C horizon. This is where we're having our bedrock broken down, okay? Gradually, over time. Now, what happens, do you suppose, when all of these randomly oriented clays are pressurized? What happens if I put some pressure on them from the top? What are they going to do? Compress how? How do flat things compress? Like this, right? They compress on top of each other in a parallel alignment. When I pressurize this B horizon, let's say that our E and A and O, that's all so heavy, okay? There's a lot of weight, and so over time, all our clays down here are going to form parallel alignments. How easy is it, do you suppose, for water to go through that? Yeah. Water can't get through all that. It's like trying to pour water through a book, right? If I held a book here and I poured water on top of it, where's the water going to go? Off to the sides. It's not going to make it through all the pages, right? Maybe through some of them, but not through all of them. Let's say this happens, and then there's an environmental shift. Something changes on the surface such that I no longer have plentiful biological material. I no longer have a lot of water. This all dries up. Gradually, wind processes remove it, leaving us a whole lot of compressed clay on or near the surface. Compressed clays that don't let water go through it very easily. Because my region dried out, I now have all of this here at the surface, and that is why Odessa floods. That's why we have terrible flash floods here. We used to have nice, healthy soils a long, long time ago. Those are long gone. What we have near the surface are a whole lot of compressed clays, and those clays do not let water drain through it very well, and so it sits on the surface and floods every which way until it can get somewhere that it can leave from. That's what our city is built on. The soil does not accept water very well. Told you we talked about that today, right? It's very on point for the conditions that we've had in Odessa the last couple of days, isn't it? Just maybe. I was telling everyone else about this earlier. I went to Walmart yesterday. I walked into Walmart about 12:30 in the afternoon. Water was up to my ankles. I walked out about 1 o'clock, and I had to go through water halfway up my thighs to get to my car. I'm not wearing my boots today. I'm wearing my sandals because my boots are still soaking wet from walking to my car in Walmart parking lot. Yeah. Your friend's house flooded? I'm not surprised. I'm sure a lot of people are in that situation.
I was at work,
Yeah.
and so I was driving to work. It was horrible.
Mm-hmm.
That was absolutely horrible. And then once I got there, it was leaking.
Yeah. Yep. What do you drive?
I was driving my dad's truck.
Okay, good. You were in a truck.
Yeah.
Good. I can't tell you how many little cars stalled out in parking lots and in intersections. Dixie and 42nd, little car stuck there. It's like an ocean out there, and this car had water up over like the driver's side windows. I was in my Jeep, and the water was like halfway up the driver's side door at that intersection. Yeah, it was a mess. The firemen, a fire truck showed up, and like water was up to here on the firemen as they were trying to push this little car out of the intersection. It was not good. All right.
I saw videos of like people like eating like floaties or whatnot, just going across the street.
Yeah, exactly. And now you know why that happens. Now you know why we have that problem here. Is that a question or a stretch? No worries. Okay. You keep faking me out like every week. Is it still like that? No, that intersection drained out. There's going to be, it's probably got some water in it still, but it's not coming down nearly as hard as it was yesterday. Okay. Now, there are over 19,000 different soils classified in the United States classification system. Why do I specify the United States? Well, because pretty much every nation has their own classification system. There is no universal one yet. Hopefully someone gets on that, because there tends to be some miscommunication there. You do not need to know any of them. I've given you the list of the 12 orders of soils here. Those 19,000 classifications fit inside these 12 orders, but you do not necessarily need to know any of these. Just in case you were interested, I throw that on there. Now, how do you suppose humans impact the condition of soils?
Taking resources.
We think everything.
It's another friend. I have a lot of friends walking past my classroom today. Sorry, say that again?
Taking resources.
We can take resources in the form of
Fruits, food.
plants. Okay. What else? How else can we impact soils? Animals can impact soils. Okay. Agriculture is a huge one. Let's think about the rainforest. Amazon, all of the rainforest, but let's use the Amazon as an example for now. The Amazon rainforest soil is very different from the soil we have here. Same components, different quantities. Also, the horizons are different. Here we have a very thick B and E. There, they have a very thick O, organic, right? There's lots of plant life. Very thin A, and then very thick E. Okay? Why? Their plants have adapted to grow fast and die. Their plants don't live for a long period of time because they absorb all the nutrients that they need from just the top layers of soil. Their roots don't go very deep at all. Look, they're tearing up this rainforest. Look, there's not a whole lot of root systems that go more than a couple feet deep. The rainforest plants generally have very shallow root systems because all the nutrients that they need are in those top layers of soil, the O and the A, and then they grow, they live, and they die, and they return those nutrients to the top layers of soil. So the bottom clays don't get used. It just gets thicker and thicker and thicker. And so under these rainforests, we have very thick deposits of clay. So you strip off that rainforest, and all of a sudden, all of that loose clay is there. And the next time it rains, all that loose clay is going to get washed away. Remember, this isn't pressurized. This is not flattened clays. This is just loose clay, just dirt. Think of it like that. And so all that's going to get washed away. And where does it go? Huh?
To the top layer.
No, where's it eventually going to go? Ah, to the ocean. This is a picture of the Amazon River Delta. It's dirty and brown. And it's going out into the ocean. And what do you think it's doing to the ocean? Let me see if I can find a picture of it going out into the ocean. Oh, come on now. Yeah, look at this one. Sad images take a minute. Hold on. But this is a picture from space, from a satellite, of all of the dirt, this clay, in the Amazon River getting carried out into the ocean. Now, what do you suppose that clay is doing to the ecosystems, not only in the river, but also in the ocean nearby? Look at that. Does that look particularly healthy to you? No. As more rainforest is removed, more clay is carried into the river system and emptied out into the ocean. That is soil that cannot be used by the rainforest, and that is severely damaging both the river and ocean ecosystems. Deforestation. They can do that. You're clapping. I'm not sure that's a clapping moment, buddy. It is very interesting. I will accept the clap for how interesting it is. Now, this soil can be used for something. It's not really ideal for, say, crops or anything like that. But this city, this is called Angkor Wat, it's made entirely out of bricks from rainforest soil. And it has stood for a very long time. Okay. So the people who live in rainforest conditions know how they can utilize that soil for some things, but you remove that soil or you remove the trees by deforesting, and all of a sudden your soil is not being held down by the vegetation, and so it can flow away. Now, what happens if we use soil too much?
Dries out.
Dries out. We utilize all its organic content. Yes? Yes, there's nothing left in the soil that other plants can use. And without soil, we can't grow crops, can we? No. the stuff that we rely on to eat. Wheat, fruit, none of that can grow without soil. It is a finite resource that you and I and every other living thing that on land anyway relies upon. Okay? We actually have an example from our history of what happens if you use crops or if you use soil too much. Okay, you ever hear of the Dust Bowl? In the 1930s, there was two things that happened. A very long history of using soil over and over and over and over, and a drought. Both these things at the same time led to what we call the Dust Bowl, which is when hundreds of millions of acres of land, all their dried out soil got blown away. And it swirled around and it blew this way and it blew that way, buried people in their cars, towns were abandoned. It lasted for a while. It was bad. Matter of fact, this fellow right here, his arm is out on this plant where the level of that plant was before the Dust Bowl, and now he's standing at the current ground level. Imagine, for 100 million acres, that much soil was removed and blown around. Yes? Yes. So as the soil was removed, the roots just continually grew down, right? And this clump of everything is being held together by the roots of these plants. Okay? So we recognize that there's a problem with mismanagement of soil. No one can deny that. Okay? No one in their right mind anyway. So what are we going to do? We got to do something. And actually, there are other ways that this can be harmful as well. Okay? For example, currently 24 billion tons of soil are lost into the ocean every year. That's a lot of soil that we can't use, and it takes a long time to regenerate. You have to break down that rock. You have to get the right mix of organic content in there. It takes time, and yet every year, 24 billion tons are lost into the ocean. A lot of that probably comes from situations like the Amazon, okay? Now, as all that soil is going into a body of water, what's it doing? Huh? What was that? Pushing the water out. Why? It's taking up that space. Let's say I've got a dam, okay? What did the fish say when it ran into a rock wall? Dam. Thank you. Okay, now I have a dam, okay? Here is my dam. Here is the level of my water, okay? Out of this dam, a little bit of water leaves, okay? On each side of my dam, let's do a top-down view, okay? So here's the top-down view of my dam. Here's the river running to it. Here's the river leaving it. But around the perimeter, let's make this an actual river, okay? Around the perimeter, I've got people living. I've got farms and communities, right? What happens is actually, there's going to be a reservoir on the other side of that dam. Okay, what happens if all the sediment, mismanaged soil in this river gets washed into this dam and it starts filling up the bottom of this reservoir from the bottom? What's the top of the water going to do? It's going to go higher. And as it goes higher, it's going to exceed the bounds of its river banks. And as it does so, it's going to move out and flood the neighboring communities and farms. Not only that, but a lot of these farms whose soil is flowing out of the farm and into the river system, a lot of them use pesticides and fertilizers. These pesticides and fertilizers usually have something toxic in them, or at the very least, nitrates. Nitrates are the favorite food of algae. You feed algae nitrates and they're going to skyrocket. You get an algae bloom in any body of water, that algae consumes all the oxygen, your fish can't breathe, nothing in there can breathe, everything dies, you have dead water bodies. Nothing's alive in there except the algae. There's a lot of potential issues that come from mismanagement of soil, okay? I hope that's what you're getting out of this. Now, let's talk about some of the ways that we can manage our soils better. Have you ever driven along the road and you pass a farm and they've got these rows of trees around the perimeter of the farm? Like this. This is called a windbreak. You know what this windbreak is doing? It's breaking wind. Not like that. Okay? No. It's taking the energy. It's taking the energy out of the wind, so there isn't enough energy in that wind to carry away your soils. Okay? Very useful in places like here where we get lots of wind all the time, right? Okay, then there's terracing. That's this picture down here. This fellow has a hill, and on his hill, he has cut steps. And on each step, he is growing a crop, or it's the same crop just continuously over and over on each step. What do these steps do? Well, as time goes on and the natural process of water falling here and flowing away and the wind is blowing, it's moving the soil, it's already going to be happening. But what these steps do is they are capturing those soils on each one of those steps. So as it's carried away from this step, it's caught on this one for some time. And then as it's carried away from that one, it's caught on that one for some time. And as it's carried away from that one, it's caught on that one for some time. He's reusing his soils over and over and over, just on different steps, depending on where it's being carried. Okay? It's not all one flat area, and the wind just blows it away. If that makes any sense. Okay. And then the last thing that I want to mention is crop rotation. Any of you guys ever grew up on a farm or around agriculture of any kind? No? Anyone want to tell me what crop rotation is?
So some like crops will take nutrients out of the soil, so they'll switch them around, and once they'll take it out, reverse it.
Yes. Okay. So one crop will take something out of the soil, and so after you grow that crop, you grow a different crop that will take that thing out of the atmosphere and put it back in the soil. So corn and beans are a good example. They complement each other very well. Corn tends to, I believe it is corn that removes nitrogen from the soil, and it's beans that put it back in. Okay? But you get the idea. So say from January to March, just as a simple example, I'll grow corn in fields marked 1 and beans in fields marked 2. And then I'll harvest, and then for July through November, I'll grow beans in fields marked 1 and corn in fields marked 2. And I'll just rotate back and forth. This is crop rotation. Why? Because I'm keeping my soil alive. I'm keeping it healthy. I am not going over. I'm not going corn until we end up with another dust bowl. We can actually thank our founding fathers for this, by the way. Thomas Jefferson, George Washington, they experimented with concepts of this on their estates. I've been to both those estates multiple times. It's actually fascinating, the history that's there. I love going there. All right. Any questions about crop rotation or any of these methods? All right, well then let me ask you this. Why do we chop down the rainforest? The wood? The wood can be valuable, and some people definitely use it, but the volume of trees that are cut down in rainforests, that's so much wood, and not nearly all of it is used. They don't take the soil, they let it just flow away. It goes out in the Amazon, remember? Farmland, homes, maybe some of it. Again, not nearly all of the rainforest that's cut down is to facilitate growth of population. Any other ideas while I walk over here to get something? No one? Let's see, where do I have this? Let's hear one more idea. Why do we chop down rainforests? I shouldn't say we. You and I aren't doing it. Why do people chop down rainforests? Ah, what resources could be under there? This guy right here. This is called bauxite. 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 You see those little pink and red and white nodules in there? That is aluminum. Do you remember what the chemical equation for clay was by any chance?
Oxygen.
Yeah, there's oxygen. Yeah, the flat minerals. This is before y'all walked in, actually.
It has water in it.
It has some,
Calcium.
Silicate mineral.
it is a silicate mineral. It is a secondary silicate mineral. But the number one most important thing to remember that it has in there is aluminum. Do you know what aluminum is? Do you know what it's used for? Oh, everything. That bottle is made out of aluminum. A substantial amount of the metal in your laptops are aluminum. The foil, the aluminum foil in your kitchen they used to wrap cookies and lasagnas, that's aluminum. Those muffin tins over there that your labs are in are made out of aluminum. The metal in your glasses made out of aluminum. A substantial amount of airplanes, spaceships, space shuttles, satellites, bicycles, aluminum. Why do we use aluminum so much?
Good conductor.
Not because it's a good conductor.
Sheet. There's a lot of.
It's light. It's extremely light, but also strong. Easy to shape, extremely light. Perfect for airplanes. Perfect for a lot of things. And yet, extremely difficult to find in heavy quantities. Aluminum is one of the 8 most common elements that the crust is made out of, but it is dispersed into so many minerals. Feldspars, clays. It is extremely difficult to find a rich source of aluminum because it's all over the place in tiny quantities. And so, enter bauxite. Those unused clays that the plants never go to utilize, right? Their roots don't go that deep. Under the rainforest, the thick deposit of clay matter, over time, all of those clays kind of compact together and their aluminums coalesce into these reddish pink nodules. That's almost pure aluminum ore. These nodules in this one sample. This is the richest source of aluminum that we know about and can mine. And that, my friends, is why the rainforests get cut down. The number one reason, sure, there's going to be some making space for human populations to move. Sure, there's going to be some, we want these trees. But the number one reason is to find aluminum ore in the form of bauxite. Now, make sure that gets passed around. There has to be somewhere a happy medium, doesn't there? There has to be some way to get the aluminum we need to continue progressing our technology and our civilization without chopping down all our rainforests. There definitely is. But right now, the cheapest option is to keep chopping and to keep mining. And so that's what people do. Now, there's more and more discontent with that. More and more people don't want that to happen. But as long as there is still money in it, people will still be doing it. This is the the answer to a lot of our problems we have in the world today. If someone would invest money into finding a different way, things would probably be better. But right now, it's not cheap to do that, so no one does. Unfortunate.
I'll find it.
You'll find a way. Thank you, Angel. I hope we can last long enough for you to do that. I'm holding out hope for you.
I'll save the plan.
Thank you.
Our savior.
Yes, we need it. All right. Any questions about today's lecture? No? Well then, the rest of the day is lab time.